Our second speaker will be Dr. Micheal Barker, Professor of Civil and Architectural Engineering from the University of Wyoming and Director of Education for the Short Span Steel Bridge Alliance. Micheal will present the case for galvanized bridge superstructures, will explain the life cycle cost implications of galvanizing as corrosion protection.
Well, I'm glad to be here. This is going to be very different than what Derek did. He talked about specifics of painting. I'm going to be talking about galvanized, but I'm going to be talking about life cycle costs of galvanized steel bridges. Again, my name's Micheal Barker. I'm at the University of Wyoming, but I'm also the education director for the Short Span Steel Bridge Alliance Bridge Technology Center. We've got to cover life cycle costs of steel versus concrete first, so that you understand what this research did. And then we're going to talk about life cycle costs of galvanized bridges. And so this started because we always get the questions, I do a lot of talking to counties and states and owners of bridges, and they always ask me, in terms of life cycle costs, which is better, steel or concrete? And the steel industry gives their anecdotal evidence and the concrete people give their anecdotal evidence, but there was really never a study on it. And so we performed a historical life service, meaning performance and maintenance, and agency life cycle cost study of steel and concrete bridges in Pennsylvania. And we picked Pennsylvania because the state engineer there offered their data and had good data. The report is on a website called shortspansteelbridges.org. So to do a life cycle cost study, you have to start with a comprehensive inventory of bridges, and you need to know the initial costs and the date built and all maintenance costs and the dates those were performed, whether they were departmental maintenance or contractor maintenance. And then, of course, because these bridges are still in service, we needed an end of service date or an end of life model. We had to be able to define what would happen to that bridge from the day it was born until the day it was replaced. And PennDOT had pretty good data on that. And then we took the PennDOT database and we wanted to look at typical bridge structures. We didn't want the weird bridges and all that kind of stuff. This is a typical bridge study where we're looking at precast I-beams or precast boxes where the boxes are adjacent or where they're spread with a deck in between them, and then steel rolled shapes and welded plate girder bridges. And we also wanted to look at the modern era of bridge construction. So, precast, pre-stressing came onto the scene about 1960. And that's also when, steel started doing a better job of designing and detailing for long-term performance. And so I looked at, I did the study, so that's why I'm reporting on it. So I looked at bridges built between 1960 and 2010. Then, of course, I needed to know all the specifics of what had happened to that bridge with costs and initial costs. And then I wanted to get rid of the very simple replacements and the very expensive bridges, that might go through some crazy valley with really crazy environmental work that had to be done. So limited it to ones with initial costs between $100 and $500 per square foot, and then just used their recorded initial and maintenance costs for those bridges. And so Pennsylvania has over 25,000 bridges. Of those, 8,500 of them are of those 5 types that I'm looking at. And of those 5 types, of those 8,500, a little over 6,500 were built between 1960 and 2010. And so this table shows the bridges out of the database that met all of that criteria for the 5 types of typical bridges. So we ended up with a little over 1,700 bridges, which represents about 26% of the potential 6,587 bridges. Now I had to come up with a bridge life model. When was that bridge going to be replaced? So I took all of the 6,500 bridges and calculated average deterioration rates, assuming it started at a 9, and I based the study on the year 2014. So I could calculate a deterioration rate by saying, what was the superstructure condition rating in 2014? And then minus 9, I assumed it was a 9 when it was built, and then divided by how old it was. And that gives us our first table here down towards the bottom, where the right column is the deterioration rate or the condition rating loss per year. And then I can calculate a remaining life, assuming that the bridge is going to be replaced when it reaches a 3, divided by the average deterioration rate. And then, of course, the bridge life is how old it is plus the remaining life. But here's our first results table. And you're going to see several of these tables, and I have two aspects of this table that we want to talk about. The first is, towards the bottom, I'm going to list the best and the second best performing bridge type for that table. For instance, here, steel rolled beam bridges have an average deterioration rate of 7.1 condition rating per year. Second was precast box spread at 8%. And then at the bottom left, you see a statement that says all are similar with none way out of balance. And I'm going to deal with that right at the end. But you can see that, yes, they vary a little bit, but there's no one that is way higher than any others, and there's no one that is way lower than any others. Okay, so now we're going to just do a quick example of a life cycle cost for a bridge. I picked this bridge in Pennsylvania. You know, it's a 3-span bridge. It's a pre-stressed box where the boxes are spread with a deck in between. It was built in 1969, and in 2014, it had a superstructure condition rating of 5, which means with an average deterioration rate of about 8% per year, I can calculate that it will get to a 3 in 25 years. And the bridge is already 45 years old, and so that gives us a bridge life of 70 years. Then through their records, I could determine all of the costs. So the top half of the slide is the initial cost and all of the maintenance that occurred on that bridge over its life so far. And it was built in 1969, and at that time it cost $141,000. And then I divide by the area of the deck so that I can compare bridges to bridges, and that comes out to $18.50 per square foot. And then the maintenance doing the same thing. Now, to compare the bridges, I had to take into consideration inflation, and so I brought all of these costs up to 2014 costs with the engineering record construction cost indices. And so this is what we're predicting that bridge would, the bottom is what we're predicting that bridge would cost in 2014 dollars if it was built in 2014. And all future maintenance are in constant 2014 dollars, because when we do the time value of money with a discount rate, that already takes care of inflation. And so now that I've done that to this bridge, I can lay out its life. I can say it's going to last 70 years, and it was built in year 0, and in years 19, 40, and 44, it had maintenance. And then I can calculate a present value cost for that thing. That to run that bridge for one cycle, the equivalent cost when it was built is $154.50 per square foot, which kind of means if we could put that away into some sort of savings account, we could build a bridge and we could pay for that maintenance in the future. However, I can't compare directly a bridge that lasts 70 years to a bridge that only lasts 40 years because the outcomes are different. And so what we usually do is we do one of two things. We use equivalent uniform annual costs, which are really hard to picture in your head, or we use capitalized costs, or what I'm calling here perpetual present value costs, which means that we assume that at the end of the life, the bridge is replaced with an identical bridge in perpetuity. And we can see that that one comes out to $194 per square foot. So again, if I had that money and I could sink it into an account now, I could build a bridge for this cycle, and in 70 years, that money will recuperate, and I can build it again, and I can build it again. And with capitalized costs, I can compare bridges directly, no matter what their lifespan is. And so I took all those bridges and I created really 3 Excel sheets. The first one being general information: location, year built, spans, length, area, geometry, materials. And then the second file was all the department and contractor maintenance performed on those bridges. And then the third was really the results: the initial, the capitalized costs, and the present value of all future maintenance costs. And now I can do a comparison. So from all this, I've produced a report. The report is quite extensive. You can find it on that shortspansteelbridges.org website. But here I'm just going to show a few of them shown in light blue. I'm going to look at bridge life, capitalized costs, and then I'm going to look at capitalized costs versus bridge length. So here's kind of the first results besides that deterioration rate, bridge life. We can see here we have rolled beams, plate girders, a box adjacent, box spread, and pre-stressed I-beam girders, the number of bridges that were in the final database, the average year built, which is pretty much the same, and then the average bridge life. And we see, according to PennDOT data and the life model used here, that steel rolled beams are expected to last the longest. Second is precast box spread beams. But again, none of them, there's only like a 7-year difference between those. So none are way out of balance. They are all kind of similar. So now this one with the arrow is the important one here. That's the capitalized cost, or the perpetual present value costs. And we can see what those values are. And for all of the bridges in the database, the precast I-beam comes in at the lowest and the steel rolled comes in second. And then the others follow that. But again, all of them are still pretty similar, with none way out of balance. But this isn't a really good table to compare, because we also have to look at some other variables there. Average length. The plate girders have a way longer average length than the others, way more spans, that type of thing. And so the report does divide up and look at these variables individually. I'm just going to look at one of them. I'm going to look at bridges with lengths less than 140 feet, short length bridges, because that's what the Short Span Steel Bridge Alliance deals with. Now, the Alliance deals with simple spans, and I did not do it for just simple spans. This is based on length. So you can see the average number of spans over here in the third to the right column. It is a little bit greater than one, except for the plate girder. The average length is much more consistent. Again, the average year built is pretty close. The average life is pretty close. And if we look at the capitalized cost for here, now steel rolled beams are the least expensive alternative compared to the others. But again, all are similar, with none way out of balance, except for maybe those plate girders. And yeah, we would expect the plate girders in short spans not to be as economical, because they can be the most economical choice about 80 foot or above, but below 80 foot, we're not going to be building plate girders. And so those costs come in a little high, but the others are very close. And so I started with, people ask me, which one is the best for life cycle costs? Is it the box adjacent? Is it the rolled beam? Is it the precast I-beam, box spread, plate girder? And this is kind of the results. And this is where I deal with that statement that all are similar, with none way out of balance. If we calculate an overall weighted average capitalized cost, it comes out to be $252 per square foot. And all the 5 bridge types are within 14% of that weighted average. Well, okay, what's that 14% mean? Well, if we look at the standard deviation within all of those 5 types, the coefficient of variation is between 20 and 25%, which is, quite a bit higher than 14%. And statistically, what that means is that any one type of bridge may be the most economical for a given bridge project, that there is no one bridge type that clearly beats the others. And so the conclusions of this first part of my presentation is that typical concrete and steel bridges are competitive on initial costs, future costs, life cycle costs, and bridge life, and that owners should consider both steel and concrete alternatives for individual bridge projects. And then the red here, there were no galvanized bridges in the database. And so the question arises, what about galvanized steel bridges? Well, we have steel girder protection systems. Derek just told you about one of them, painting. We have weathering steel. We have galvanizing. Kevin's going to talk about metallizing. And then, of course, if we really want a fancy corrosion system, we go to stainless steel bridges. But that's kind of cost prohibitive, except for very corrosive environments. But galvanizing certainly has become an economical and effective protection system. The initial costs are about equal to, and sometimes even less than, a quality 3-coat paint system. Sometimes they're more expensive though too, or galvanizing is more expensive. It depends on the market and where you're getting it done. But it does significantly increase the life of a steel bridge, and it also reduces future maintenance. And so I performed an additional study where the objective was to develop useful owner information on effects of galvanizing on the historical life cycle costs of typical bridges. So I'm taking the one we just went through, and now I'm going to look at it again and consider galvanizing. Now, this work was actually sponsored by US Bridge out of Cambridge, Ohio, because they were trying to convince the Puerto Rican authorities on galvanizing after Hurricane Maria, and they were successful. What did I do? Well, I said the benefit of galvanizing is an extended life and reduced future maintenance. And so I took the painted girders out of the PennDOT database, and I have their life cycles with their maintenance and their expected life. And then I said, if we had galvanized that, let's pretend that we galvanized that thing. What does that do for us? Well, I added 25 years of life to the bridge, and I took out the maintenance, the painting type maintenance, or replacement of girder maintenance because of corrosion. Now, where did I come up with this 25 years? This is kind of a guess, right? But I needed a rational value to say, if this had been galvanized, it would last longer. How much? I came up with 25 years by looking at hot dip galvanizing, time to first maintenance data, saying that, well, bridge, I think the minimum is actually 3.9 mils. And coming up here and looking at suburban steel in a suburban setting, and that comes out to be 95. And if we expect our bridges to last 70, that's about 25 years. And if we look at rural, I mean, that's way up there. So that's one reason I came up with 25. Another one, again, anecdotal evidence, is that the first galvanized bridge was the Stearns Bayou Bridge, built in 1966. And they did a study in that thing in 1997, looking at the mill's thickness and the product and all that kind of stuff. And they said, hey, this thing has 66 more years to it until first maintenance. Well, that gives us an expected life well over 105 years, and this is a picture of it, and that's not in a friendly environment. And so that's how I came up with the 25 years. And so now what did I do to the database? I took all the painted steel bridges in the database, and I modified them by assuming that the steel had been galvanized instead of painted when built. The assumptions I used was that galvanizing adds 25 years to each of the individual bridge lives. Galvanizing costs are the same as a quality paint system, therefore the initial cost did not change. Future painting costs are removed from the maintenance record, and corrosion repairs to the girders are removed from the maintenance record. But I did keep in the other maintenance, if there was a concrete deck replacement, if there was joint repairs, and other maintenance work still stayed in there because that doesn't depend on galvanizing. And so here's an example. This is kind of a severe example because this bridge corroded faster than it should have, and they actually had to replace the girders. But here's one, again, 3 spans long, 220-foot length. In 2014, it had a super condition rating of 6. So I could predict, with the deterioration rate of part 1 of this study of 7.1%, it would last 42 years, and this bridge came out to have a 83 predicted life. For the painted bridge, for the galvanized bridge, I added 25, 108. Here are the bridge costs, the actual costs and the actual years, and then of course using construction cost indices to bring them up to the year 2014. For the painted bridge, there's the initial cost, and then in 29, they had to kind of replace steel girders because of corrosion, which was expensive. That's why I'm saying this one's kind of an extreme example. That wasn't common in the database to replace the steel girders. For the galvanized, it's just the initial cost. And that's another reason I picked this one, because there's no deck replacement to make it complicated. So I brought them up to equivalent 2014 costs and then laid them out. Here's the life cycle for the painted bridge, 83 years, 1 maintenance, initial cost. Here's for the galvanized, lasts 108 years, get rid of that maintenance cost. So the present value cost for 1 cycle for the painted is the initial cost plus the discounting of that maintenance, comes out to 140. And then I can also calculate what is just the present value cost of that future maintenance. That comes out to be 18.5 bucks per square foot. Okay. Present value cost for the galvanized bridge is just the initial cost. Then of course they have different outcomes, and so I have to do capitalized costs, and The painted bridge comes out to 165. The capitalized cost for the galvanized bridge drops to 133. Okay, so now the results. The top table here is for all the bridges, all the steel painted bridges, and all that's rolled and plate girder, and all the steel bridges galvanized. And here's an important column here: lower capitalized costs. Went from 265 down to 242 and a third. But we can also see we have lower future costs. They're cut in half because of the maintenance that is not required for the galvanized bridges. And of course, longer life, and that's always going to be 25 because that's what I assumed. Now down here in the bottom, I divided it up. The top half of this table is for the rolled beam, the bottom half for the girder, but we see the same thing. That capitalized costs are reduced significantly. Future costs are reduced significantly, and of course the bridge life. Now I want to compare that back to what we did in the part 1 of this study to concrete bridges. Here we see overall steel painted. I'm only looking at the I-beams. I took out the plate girders because they're short length bridges. So here's a repeat on the top of rolled beam results. But now we compare them to the concrete results. And here we see that now we had a little flip here on this bottom left. Overall, because the overall database had quite a few weathering bridges, steel rolled beams were number 1 with the precast box spread number 2. When I took out the weathering steel and took out the plate girders, precast box spread actually took number 1 place with steel painted, or with the steel second. Here, steel galvanized is the least cost, then comes precast box spread, and then steel painted. And you can also see the benefits for future costs, present value of future costs, and of course for life, since I added 25 years to the galvanized bridges, those are definitely going to be number 1. And then second was steel painted, and third was precast box spread. So conclusions from the assumptions made here, the rational assumptions, but assumptions made here, and the real database of the PennDOT bridges, galvanized bridges have significantly lower capitalized costs and last 25 years longer compared to painted steel bridges using rational assumptions. And then for all painted bridges, it's a little bit over 8%. For painted bridges with a max length of 140 feet, well, yeah, it's still a little bit above 8%. And for all painted bridges, because I just took this as one value, galvanizing reduces present value of future maintenance costs by about 50%. And then also important is the reduced capitalized costs also results in steel bridges being more competitive compared to concrete alternatives. For all the steel bridges, galvanized steel is less expensive than the best concrete by a little over 3%, versus painted steel is a little bit more expensive than the best concrete by about 5%. And for the shorter bridges, 140-foot max, rolled beam bridges, galvanized steel is less expensive than the best concrete by over 6%, whereas painted steel is just slightly more expensive than the best concrete by a little less than 2%. The summary is galvanizing is economical for first costs. Not always, but can be. Extends the life of the steel bridges, reduces future maintenance costs, and can lower agency life cycle costs. So that is my presentation. I thank you very much. Again, you can find the full report for both the overall life cycle cost report, an additional report that shows a complete representation of this galvanizing study on shortspansteelbridges.org website. And with that, I will turn it back over to either John or Mike.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.